but we call doing this to a function, we call the answer f prime of x, and it's called the derivative of the original function. So it's the derivative of f of x. When you take the derivative of a function, you call it f prime of x. That's what you call that, f prime of x. And that's what you do. That's the derivative. And what does it mean geometrically, graphically? What is it? The slope of the tangent line. You know, we could say it's the slope of the graph, but, you know, people don't think of, well, what's new is the slope of a thing that curves. How do you talk about the slope of a thing that curves? Well, you talk about the slope of its tangent line. That's what you do. I mean, how can you talk about the slope of something that's curving? Well, at any point, there is a tangent line. And if that point moves, that tangent line is different. So what it is I can talk about the slope of a curve, but it's the slope of the tangent line, and it's changing all the time. As you can tell, it's changing. It's a changing slope. So what is the derivative? Geometrically, it's the slope of the tangent line to a function. You know, slope of the tangent line at any point x. Sometimes I try to keep the words to a minimum, but that's what it is when you do this. The slope of the tangent line at any point. It's pretty cool. It's a little formula. It's a new function. It's its own new function. It's the derivative of some original function, and it's the slope of the tangent line. There's other ways to talk. Maybe I'll wait until I get on into chapter 3 more. Maybe I don't need to explain everything today. But there's other ways to talk. Because it's a slope, it is a rate of change. And we can talk about, if it really was 2 points, that's an average rate of change. But when it's at 1 point, it's like an instantaneous rate of change. It's change at one particular instant. Of course, that rate of change is changing, I guess. So there's other language, there's other ways to talk. Slope is a rate of change between two variables. There's some other notations too. You know, I wrote this notation for the derivative of a function. If the function was called y, you might call it y prime. Another notation is dy dx. That's dy over dx like that. That's the notation of a derivative. So I'm not really testing you on all that Friday, okay? We need to get into that next week. But I think I want you to do this limit, and maybe I'll ask it in this way. Watch this. Watch this. Maybe I'll ask it in this way. Find the slope of the tangent line. Actually, maybe I want the slope. Yeah, okay. Find the slope of the tangent line to this function. At x equals -3. So that's a good question. You guys want to try it? Let's try it. First of all, when you read it, I guess you got to have this memorized, because I mean, if it says find the slope of the tangent line, so what the hell's the slope of the tangent line? I guess you better know the slope of the tangent line is this derivative. And how do I do a derivative? I do this. So I got to do this. So maybe you should know this. All right, I want to do this. Here's what that means. I'm going to do the derivative. I'm going to do the limit as delta x goes to 0. And I'm going to do f of x plus delta x, which you guys go to your function and plug in x plus delta x, right? Go to your function and plug in x plus delta x. That's that. That's only that part, right? Go to your function, plug in x plus delta x. Minus the function itself. Minus the function itself with just an x in it, which is just the function itself. Okay, When I subtract something, I put a parentheses around it. I'm going to distribute that subtraction and subtract all those terms, and then it's all over delta x. So setting up this limit is sort of the first part, and then doing it is the next part. But setting up this formula, reading this and understanding how to set this up is kind of important. You know, hey, what did I always say is step one of a limit? Plug it in. If you do let delta x go to 0, and you did try to plug it in, you'd find 0 over 0 is what you would find. You'd get and so we've learned that that needs work. So anyway, I'm not going to really bother. This is a 0 over 0. This needs some fixing. And the way we fix it, we've learned, we've done problems like this a couple times. Foil this all out, distribute, things cancel. Eventually, this delta x will cancel. Eventually. That's kind of the last step. And then you can do the limit. Then you can do the limit. Do you want me to help you? All right. So I'm foiling out first, then distributing the 5. Don't do that backwards. And then if you don't mind, I'm going to do it all in my head. So if I foil this out, I get an x squared. But when I distribute the 5, it'll be a 5x squared. You know what? I'll get a middle term that's called 2x delta x. I've tried to teach you that you treat that delta x like a separate variable. And so you get an x times a delta x, you get 2 of them, then you multiply by 5, you get 10x delta x. Then you get a delta x squared, and it's multiplied by 5. So I just foiled it out and distributed the 5, all in my little head. You all right? Good morning, by the way. Good morning. Let's do some math. All right. I did it in the wrong order. Let's do some math and then good morning. Cool. Distribute the 7. Minus 7x, minus 7 delta x. Don't forget the plus 8 is there. I mean, that's that. Distribute that negative sign. Negative 5x squared plus 7x minus 8. It's all over delta x. I mean, it's a long problem. It's long and a little bit tedious, but if you know how to foil and try not to make and distribute, and you'll be fine. And now, like we said, things cancel. It's pretty typical. They're all kind of work this same way. I think that 5x squared cancels with that negative 5x squared. I think that negative 7x cancels with that positive 7x. I think that plus 8 cancels with that negative 8. It's so awesome. What's left is these 3 terms, and they all have a delta x in them. The kind of that you can kill a delta x or factor or cancel a delta x. The way you kind of do it is you factor it out and then cancel it, I suppose. You following me? I'll factor it out. I'm left with a 10x plus a 5 delta x, when I factor it out, minus a 7. I factored out a delta x. It's all over this delta x. Now I'll cancel those. And now I'll do the limit as delta x goes to 0. See, this is not quite the answer. I haven't done the limit yet. When I do this limit, this delta x will go to 0. And what's the final answer? 10x minus 7. And that's called the derivative. That's f prime of x. It's 10x minus 7. And what is it? It's a new function. It's the formula for the slope of the tangent line to that original function. This is the derivative of that function. He's a formula that tells me the slope of the tangent line to that original function. That's what he is. Said it 6 times. Yes.
One more time.
One more time? So when you do a derivative, you get this new function. And it's the slope of the tangent line. It's a little formula that gives you the slope of the tangent line to the original function.
So would you now just plug in that -3 to that to find out the answer to that?
Thank you. So this is the slope at any point x. Look over here. When I do this derivative, it's kind of at any point x. That's an important thought, right? It's this formula for any point x. So I got the slope. If I want the slope when x is 1, can you tell me the slope when x is 1? Thank you. When x is 2, tell me the slope. Thank you. When x is 4, tell me the slope. Bam. You know what I'm saying? You got a cool little formula here. Boom. You can shout them all out. I guess I did ask this question. So now I'm going to say this. F prime of negative 3. You know, that's me sticking a negative 3 into the derivative. And if I stick a negative 3 into the derivative, it's negative 30 minus 7.
Yeah, negative 37.
Negative 37. Well, I guess that's my slope at this point. Good, right. At the end, we should plug in. You get this formula, and then you can plug numbers in if that's what you're supposed to do.
So it should be a good idea to plug negative 3 into that.
Early.
Early, yeah.
Yeah. Well, you know, no, except if you were reading the book, in section 3.1, there's an alternative definition to this. Yeah, and I don't really want to get into it, but you can, there's an alternative definition where you do the derivative at some point C.
Okay.
And then it's a little bit different. You do plug the C in early, and then at the end at the end of this problem, you would have got negative 37. I don't want to do that. Is that
Yeah,
so
I
I like,
didn't know when to use that.
well,
That was really...
there's some homework that makes you try to use it, but
Okay.
I don't need it. Listen, what I can do is I can do this derivative in general, that's what, at any x, and then if someone gives me an x, I can plug it in.
At the end.
Not early, but at the end.
Yeah.
I mean, do the derivative in general like this, and then when someone says, what's the slope at x equals negative 3? If they give you a specific x, then please plug it in and give them a specific answer. Right.
Okay.
So, maybe that's a question on Friday's test. And the idea is, you got to come up with this out of your head, I guess. I mean, you got to know what you're doing here. Did you want to ask me something?
I was just going to say, I was going to be sure that it's possible for you to ask the question without adding x equals negative 3.
That's true. So, right, that's kind of true. If I said find the slope of the tangent line to this function, and I probably should say maybe in general, or that's one way to say that, or at any x, you know, I should add that phrase maybe, but then that would mean stop here, you're done, I guess. Yeah, that's called doing the derivative. That's the derivative. Yeah. Maybe I would change the language to, instead of find the slope of the tangent line, maybe I would say find the derivative. That would be this, right?
Okay.
I mean, there's a lot of synonymous language here. There's a lot of, the derivative is the slope of the tangent line. I can use either. I can use either words, sets of words. I'd like to use, I'd like you to know that they're the same, right? Hey, one more little thing though. We did this yesterday, and I just want to add this because maybe this will be Friday's question. I'm not sure yet. Same thing. Watch this. Same thing, but maybe I say this. Let's get back to what I had here. Find the slope of the tangent line. Watch this. Instead of slope, what if I say find the equation of the tangent line? So that's a popular question, and it's just subtly different. The equation of a tangent line is, you know, the equation of the line, y equals mx plus b, maybe. The derivative is not the equation of the tangent line. The derivative is just the slope.
Yeah.
And so if you're, hang on, back to this. If you're at x equals negative 3, I mean, to do this, I have to be at a certain point. So then you find okay, sorry. If you want the equation of the line, you need the slope. If you need the slope, you need to do the derivative. So here you go.
Right.
And then at this point, you plug in this point and you get Negative 37, that's my slope. So now I'm ready to do the good old equation of a line, and that makes me think of y minus y1 equals the slope times x minus x1. And I'm actually missing something. I got this slope, I'm going to fill that in. I got this x value, negative 3, but I'm missing one thing. Oh, I need a y value for my point. My point, there's my slope, and I got this negative 3 comma nothing. I don't know, I need a y value. How do I get a y value?
Plug it into the original negative 3.
Thank you. So of course, when you plug negative 3 into this, you get the slope. This is the slope, the derivative. When you plug negative 3 into this, you get the y value that I need.
Right. Or negative 3.
The y value I need. You know that. If you got an x and you need a y, you need the original function. Some students get funny. They get debating about this. There should be no debate. If you want the slope, please plug a number in here and you'll get the slope. If you just want a y value, please plug a number in here and get a y value. And it shouldn't be confusing, but students get a little weird about that. But I need that. So here I go. Now I'm plugging a negative 3 into here.
74.
Thank you. Did I trust in you guys? 74, you said?
Yep.
Yeah, I like that. All right, 74. So now I got a point and a slope. I'll do the equation of the line. I didn't lose you, did I? You guys okay? You all right? Okay. All right, y minus 74 equals the slope and x minus negative 3. All right, so I like to clean this up. You know, this is just little algebra here. Negative 37x, that's actually plus, but then I multiply by this. So it's going to be negative 111.
Right.
I'll be darned.
That comes out.
And add a 74.
Comes out to negative 37.
No way.
Negative 37.
No way, no way, no
Is
way.
what now?
It comes out to one.
Negative 37?
Oh,
Yeah. Yeah.
All right, you need to play the lotto tonight. Can you play negative 37? You can't play that.
Good stuff.
No, I don't know. Yeah, it's just coincidence. Students are funny. I mean, you know, in a math class, I mean, math is about seeing patterns and stuff. It is. And trends and patterns, you see them in math. But anyway, but don't see false patterns. I mean, this ain't no pattern. I mean, the y-intercept does not always match the slope. No, it just was coincidence. Not a pattern.
This is the problem you made up.
I did make this up. Right. Right. I just made up a function and made up a point. But I guess I've sort of done a good job of reviewing the ideas in 3.1. Here's the problem. The problem is it gets tougher depending on this function. I mean, here we did this for what we call a nice quadratic function. If you did this for a nasty square root function, it would be kind of worse. This limit would be worse. It'd be worse. And you'd have to do the conjugate or something like that. If you did this for a fractional function like this, yeah, it would be worse. I mean, you would do this, it would be worse. Again, because it's a fraction, you would do a lot of common denominator work and so forth. But it's all doable. It works. It's just tougher than this one. This quadratic one we did was kind of medium to easy.
For the test, do we have to worry about it?
Well, yeah, I don't know, right? I haven't written the test. Am I going to be,
What did she ask?
Well, I just said I can make this problem worse. With different types of functions, this process gets a little worse.
Oh, yeah.
All right, so she's worried, should we worry about that,
Well,
she
we should
said.
practice now.
Well, we could practice another one. I mean, I told you what to do. Let's do it. You want to do this one? Let's do this guy's derivative. How do I do this guy's derivative? I do the limit as delta x goes to 0. I do f of x plus delta x. What's f of x plus delta x? 1 over x plus delta x minus 4. So you got to know how to plug x plus delta x into your function. I think I just did that, right? I plugged x plus delta x into my function. That's that. Minus the function itself all over delta x. And so then what I told you is you got nasty fractions kind of within fractions. The strategy for cleaning this up is a little worse than my last problem, but it's just a little worse because it involves getting a common denominator and doing a little flipping, and you know what I mean?
Right.
I mean, the algebraic steps tend to be a little worse for students, but it's nothing you can't do. It's out. It's
Number
out.
10 on that practice test you gave us.
Right, maybe.
Like that. It's 3 over 2 minus x.
Yeah, you're right. That's a tough one. That's tougher than 9. What it? You want me to finish? You're right. It's like that one. Here's another one though. You want to finish this one, you guys?
Yes.
Okay. So how do you do this? Watch. I would say in the numerator you need a common denominator, and those are very different denominators. So the common denominator is that quantity. Oops. That quantity multiplied by that quantity. I mean, that's what the common denominator is of two different things. It's that guy times that guy. So that's the common denominator of the numerator. And then what do I have to multiply him by? The x minus 4. And then it's going to be up here and it's going to subtract. What do I have to multiply him by?
X plus delta.
The x plus delta x minus 4. I put it in parentheses when I subtract something. It's important. And then it's all over this delta x, which is sort of over 1. I mean, now you're home free now. I mean, I said this was a harder problem. It's only harder because you got to get a common denominator, and some people don't do too good with that. But it's really not too bad now. I'll help you here. That numerator cleans up beautifully, doesn't it? If you distribute the negative sign, do you see it? If you distribute the negative sign, you get a negative x. That cancels with this x. You get a positive 4. That cancels with this 4. And I'm left with a negative delta x over this nasty denominator. And then what am I going to do with it? I am going to flip it up and multiply. I'm going to flip it up and multiply. Which now, those guys cancel. And I'm left with this. Now keep in mind, I got just a little sloppy. I got just a teeny bit sloppy, but out in front was a limit as delta x goes to 0, and I'm ready to do the limit. I'm finally ready to do the limit. But did I lose you on that algebra? I hope not. I mean, get a common denominator, flip up this denominator, clean up. It's right there. It's good. It's algebra. It's good algebra. But here I go. To finish this, you do this limit, and this little guy goes to 0. And if he goes to 0, we're done. The answer is a negative 1 over x minus 4 squared, you could say. And that is, what is that called?
That's the derivative.
That's the derivative. I can call it f prime of x. The original function was f of x. This is his derivative, f prime of x. Looks kind of similar, but it's different, and it's a new function. So you're right on your number 10, and I don't, I just did one sort of similar, so maybe I don't want to do another one. But your number 10 on your practice sheet was, I'll just tell you the answer. I think I got 3 over 2 minus x squared.
Yeah.
That was kind of a good one. What was the answer to number 9? Anybody did number 9? 2x minus 2? Yeah. And by the way, those are derivatives, although the question didn't say do a derivative. The question just said do this limit. The question just said do this limit. We now know that that limit is important and means something. It's the derivative. But
I was having issues with number 7.
sure, 7 is tough. Let's talk about it.
I started flipping through all these different.
So I think it would be good if you knew this for Friday. The sine x, the limit, this famous limit, the sine of x over x as x goes to 0 is a 1.
Right.
Right.
The key to this is that this thing's going to 0 and that these things kind of match right here. And then, so if that's the case, if that matches that and it's going to 0, you can call this thing a 1. I mean, right. Watch, I'll just show you. Here's an alternative version of this. Watch this. I've put this on the test before. I mean, this looks different, but if you think about it here, I mean, you might say, wait a minute, you ain't going to 0 now. Well, you're right. I'm going to 3.
Right.
But a 3 makes this go to 0, and it makes this go to 0. This actually is the same thing, sort of translated over 3 units. If you wanted to think like that, that might not be a way to think, but it is accurate. It's the same idea, translated over 3 units. Anyway, that's also a 1.
That's also.
I mean, there's nothing to do except realize that's a translated version of that theorem. Yeah. We've also learned that if it's like a 5x over a 5x, that's a, right, you guys? This matches this. We can call this a 1. So it starts as that formula, but then it's kind of adaptable to other scenarios here. Now, let's get to her question. Her question was 7, which was kind of a good one. Who knows? I'm saying somewhere in number 7 we might use this. That's what I'm saying. But what is it? It's 8 sine 3x over 3 tangent x. 8 sine 3x over 3 tangent x. Huh. Take the limit as x goes to 0, I guess. Okay, wow. Wow, wow, wow. Let's see.
Would you
What-
change
oh.
the tangent to sine over cosine?
Probably. Good.
I do.
Hang on. Wait. Step 1?
Plug in.
Oh yeah, plug it in. I almost forgot step 1. Anyway, it's kind of stupid because step 1, usually on a lot of these, is giving me
0, 0.
0 over 0. So then you move on. You got to fix it, right? By the way, though, if you happen to do step 1 and get an answer, right? Step 1 is plug it in. If you happen to get 6, I guess you're done. The answer's 6.
Right.
Right. Or if you got 0 over 7, that's a 0. Right. But we keep getting this 0 over 0, and we keep having to do some work, right? Fix these limits. So you're right. And then her suggestion was, hang on, her suggestion was, can you make this sine over cosine? She's right. That tangent is a sine over cosine. That's good to know. This 3 is still kind of sitting here. Now maybe I'd like to flip this up. If I flip it up, I multiply by cosine over sine. Is that what I did?
Yeah.
The problem is these sine functions don't cancel. Why not?
Because they're
Because
not the
that's
same.
3x.
Yeah, because he's got a 3x and he's got an x.
Mhm.
All right, well, anyway, where am I now? I got an 8 sine 3x. I got a cosine x. And I got a sine x.
With the 3.
Oh, sorry, and there's a 3 down here. Yes, thank you. And I'm trying to do the limit as x goes to 0. All right, well, anyway, changing tangent to sine over cosine and flipping it up led me here. All right, I got more work to do. And I got another comment quickly. I said this once in class. You know, this thing is a 1. And so it works upside down, by the way. It's a ratio It's a ratio that's approaching 1. So if it's upside down, if you had the limit of x over sine x as x goes to 0, that's also 1. So I feel like, you know what I want, man? I mean, to get this to work, I wish I had a 3x. This has got a 3x. I wish I had a 3x. I got a 3. Can I multiply the denominator by an x? I can do this stuff. I can manipulate. I can multiply the denominator by an x. Now that's only legal if you multiply the numerator by an x. So I'm going to multiply the numerator by an x. Look, I'm going to put it right here. I can put it anywhere. It's all multiplied stuff. But now I've grouped this together, and I would say that's my theorem, dude. That's a 1, don't you think?
Yeah.
And I'm going to group this together and call that my upside down theorem. That's a 1. Are you following me? I needed an x in the numerator, an x in the numerator and the denominator, and now I'm done. That's the theorem. That's a 1. That's the theorem. That's a 1. When x goes to 0, those go to 1. What about the cosine of 0?
That's 1.
That's a 1. And it's multiplied by an 8. What's the final answer here? 8. That is cool. Hey, I need my 2-minute break.